Okay, so thank you so much for the introduction, and thank you everyone for coming. I'm super excited to be here to talk to you on a series of work that we have been doing on the directions of learning structured world models from the robot's interactions with the physical environments, and for the robots to do better physical interactions with the environments. The first half of today's talk will be about an overview about a series of work we've been doing over the past few years, especially on trying to learn structured world models for the robots to do deformable object manipulation. And for the later half, we'll be discussing some of the more recent progress we've been doing on this direction. Especially, we're going to share with you some unpublished work that shows you how we can leverage those structured world models to really getting us this scalable data engine and also scalable evaluation engine. So let's get started. So recently, we have seen a huge amount of progress in the fields of robotics. In certain, at least restricted areas, robots have started to become on par or surpass human capabilities. For example, the humanoid robots like doing very agile motions in different kind of environments, and also in the self-driving domain. Although we haven't really seen a massive deployment of self-driving cars yet, we definitely have already seen the deployments of those cars in different cities across the world. But what about complicated physical interactions with the environment? So how far are we in achieving human-level robotic manipulation capabilities? You are in academia. You probably have seen many videos where the robots are doing interesting interactions with the environment. But whenever you go to any industrial expositions, like ProMat or Automats, you'll be amazed how many boxes you'll see. You just see oceans on oceans of perfectly shaped boxes where the robots are moving around. So this is the current state of what's actually being deployed in the industry, which actually is pretty basic and pretty rudimentary compared to what we actually want the robots to do. For example, we humans can actually do much more than that. We can crack eggs, spread butter on a piece of bread, making dough, and making sushi. All of these capabilities goes far beyond the reach of the current robotic systems. And I would like to argue one of the key difference between the current robotic systems and with humans' physical interaction capability in this idea of intuitive model of the environment. We have this intuitive physics imagination capability. We can predict how the environment would change if we apply a specific action. For example, how the dough will change its shape and how the onion pieces will move around. And it's exactly this type of predictive ability that allows us to plan our behavior in order to achieve some target configurations. Here's how more specifically it looks like. We have a planner that takes the observation from the environment, and we are planning our action in order to achieve some target's objective. And within this planner, we have this intuitive model that takes the current observation and action as inputs to predict the evolution of the environment. So this type of predictive model actually is quite fundamental in many different areas of robotics and many different kind of real-world systems. And in order to build this specific intuitive model, or more precisely, it's essentially a predictive model. There are generally two extremes you can think about. On the very left is model learning. We have some very impressive results recently from Google, like Genius 3, that give you action conditions to the video prediction. It is quite amazing in terms of the spatial and 3D consistency in terms of the generated video. But if you look at the results, you'll realize a lot of their results look very gamish, and it doesn't involve more complicated physical interactions. It's more in the navigation domain, which actually limits their application in the robotic manipulation community. And more specifically, because I'm guessing, many of the data they use to train their model is from game engines, which we know is not accurate enough for the physical interactions. That also further limits their applications in robotic manipulation tasks. On the very right side will be the directions of adding more physics. There's a very impressive work from NVIDIA, NVIDIA Warp and NVIDIA Newton. Let's start from the first principle, build from the physics rules and give you very generalizable and robust like a physical environments. But the limitation of this approach is it typically require full state information and full parameter estimation from the environments, which often the case is not available, especially if you are doing manipulations where there might be clusters or occlusions that are involved. So what's in the middle? So that's something that we have been thinking about for years. Like once you're trying to identify the recipe, they have the right amount of physics and the right amount of learning and give us these scalable recipes that allow the robots to do physical interactions. And over the past number of years, we have like a doubling down and making a lot of progress on the direction of using graph neural network, specifically building this graph-based neural dynamics models that have the right merge and combination between the structures of the environments, as well as the learning capacity that fits to different kind of complicated objects. So like I mentioned, we have tackled tasks like deformable object manipulation, closed manipulation, rope manipulation, elastoplastic object manipulation, and also multi-object interactions. And this thread of work is really trying to leverage this structured world model that both simulates the interactions between the robots and the objects, and be able to use this type of predictive model to plan the robot's behavior. Like the key idea is to represent environments using what's considered as particles, which is essentially a bunch of points or point clouds representing the overall geometry of the objects. This, arguably speaking, is a very fine levels of representation and abstractions, and give you very good generalization capabilities and flexibilities in modeling objects of different shape and different materials. And we're instantiating a graph that models their interactions, where the edges between particles within the same objects will actually be treated differently, for example, of the edges that are modeling the interactions between different objects. And specifically, we have our dynamics model, F, that takes the current state Z and the action U to predict the next state and Z at t+1. And our graph-based neural dynamics model will model the environment as a graph. And in this case, we have 3 nodes and 3 directed edges. And our graph Z composed of the edge sets E and also node set V. And then for each edge inside this graph, for example, going from node B to node A, we take this information from both the sender B and the receiver A to get the representation for this specific edge, EK. And then for all edges, all nodes inside this graph, we'll aggregate all the informations on edges where node A is the receiver. Together with the information on node A, we will update the representation on node A. And then we have the updated representation on the edges and also the updated representation on the nodes. Then we can define the objective functions we care. For example, in this case, we care about the evolutions of the environments. So we can compare the predicted next state and the actual next states and be able to optimize this graph-based neural dynamics model. One thing I want to highlight here is that the node encoder and edge encoder, they are shared among all nodes and all edges. So this neural model can naturally generalize to systems that are larger or even smaller than during training. Here's just some results that I would like to share. On the left is the ground truth. On the right is our model's open loop future prediction, where the inputs are only the initial states, like position velocities of all particles at the first frame. And our model's open loop prediction on the right matches very nicely with what actually happens shown on the left. Here are just some more examples where we are using 2 cuboids to mimic the 2 fingers of a paleo jaw gripper, or trying to shake a box of fluids. Here, the inputs are the control commands of the container, and our model can predict very realistic waves of the fluid particles and generalize to systems that are larger than during training. For example, here we have 2 times more particles than during training, and our model can very nicely preserve the incompressiveness constraints and density constraints. It can also be applied to real world like objects. Here we are showing some of the instantiated graph for ropes, granular objects, box, etc. We're using this graph-based neural dynamics model to model their dynamics. And one thing I want to highlight is that we have applied this lines of work on very challenging elastoplastic object manipulation, specifically at making dumplings. Dumpling making is a very challenging task that involves a lot of tools, and it is also a very long horizon task. In this work, published at Coral Conference on Robot Learning, which was also awarded the Best System Papers Awards. We have these robotic systems equipped with 15 different 3D printed tools. And the robots will take these tools as the tool to do the interactions with the dough. And in this environment, we have 4 cameras looking at the environment to provide the robots with visual feedback. And the robot is working in this red area. And the key for this work is to be able to learn this dynamics model that predicts how the shape of the dough will change when you apply a specific action using a specific tool. And what we do is we did not using any simulation at all. All the data is collected in the real world environments. We just allow the robots to use those tools to do random interactions with the dough, and we collect the data. And based on this data, we'll be able to learn the dynamics models for the robots to predict how the dough shape will change. And one thing to highlight here is because we use graph neural network. We have these natural structures where the node encoder and edge encoders are shared among all nodes and all edges. So it allows very simple, efficient learning, where for each tool, we only require 20 minutes of random real-world interactions. And that's sufficient data for us to learn a decent dynamics model for the robot to do planning. Here's how the dynamics model looks like. In the middle, we have this graph-based neural dynamics model. And here the first row shows our model's open loop future prediction. And the second row shows what actually happens in the real environments. Here the blue dots shows you the shape of the dough, and the red dots shows you the shape of the tool. You can see our model's open loop prediction aligns very nicely with what actually happens in the real world environments. It can also apply to many other type of tools, like the presser and roller, where our model can correctly predict the area of the dough will be enlarged as you roll the dough around. And then we're putting this system together to use this predictive model to plan the robot's behavior. And here's how the system looks like when manipulating this dough into a dumpling. And the interesting thing about this video is there's a person constantly perturbing the robots from doing its job. And the robots has to be robust to this type of external disturbances, meaning the robot has to take real-time visual feedback from the environment and make decisions at 2 levels. At the high level, the robot is making discrete decisions, specifically what tool to use. And given the tool, the robot has to make decision what continuous action to take in order to manipulate the dough into the next task stage. So this is also a type of task planning and motion planning put together. And the key enabling factor is this learned dynamics model. This learned dynamics model predicts evolutions of the environments, which is specifically a type of forward model, like what's gonna happen. And this forward model allows us to solve this inverse decision-making problems. Here's the inverse decision-making problem will be what tool to use and what action to take. Here's what's really interesting. After the robot cuts a circle, the person shows no mercy, destroy everything. And the robot knows to start from the very beginning and reduce the whole manipulation process in order to be robust to this type of external disturbances. This shows a lot of system level considerations, and especially this learned dynamics model that allows this to happen. We compare with the state-of-the-art deformable object simulators like material point methods. We realize even with extensive system identification, the learned dynamics model, because there's no sim to real gap, it's only learned from the real data. The learned dynamics model is noticeably more accurate than even the state-of-the-art deformable object simulator, even with system identification. And the same framework can also be applied to many other deformable object manipulation. In this case, we apply it to granular object manipulation. It's exactly the same type of graph-based neural dynamics model. It allows us to predict how the distributions of the granular pieces will be moved around when you apply a specific action. Similarly, given this kind of forward model, we plan the robot's behavior in redistributing the granular pieces into achieving different target configurations. You probably have already starting to realize what the target configurations are. It's all the letter shapes from letter A to letter Z. I want to emphasize that this is a highly non-trivial task, which involves some non-trivial redistribution of the object pieces. And after that, you have to align the fine-grained details of the object pieces arrangements with the target configuration in order to accomplish this type of task. And the same graph-based neural dynamics model can also be applied on multi-object interactions. In this case, we're modeling how the object will interact with each other when you are doing this kind of stowing task. Our model can also provide you with this predictive power for you to do inverse planning. And after this many years, like many of our lessons actually summarized in this recently published Science Robotics paper, where we reviewed more than a decade of research on learning-based dynamics model for the robots to do physical interaction. And this paper actually has some very special personal connections with me, because the structures of this paper is built on top of my PhD thesis. It's essentially an extension of my PhD thesis and give you an overview of what actually happens. And in the learning-based dynamics model, we are also summarizing a lot of interesting lessons that we summarized over the years, which will be an interesting read if you are interested in this area. So then we are starting to asking the question, like, what's next? We have this graph-based neural dynamics model, the neural dynamics model of the environments with the right amount of structures, which already unlocked a lot of capabilities for our robots to do physical interactions. And there are several directions we want to go. And obviously, we want to manipulate more complicated objects for more complicated tasks. We want to also model more heterogeneous type of interactions. And what we really want to do is try to identify the recipe that allows us to scale up, not just on this tabletop lab settings, but really leveraging those in the wild videos, like OpenX and Joyce. For any of you who are following the developments of robotic foundation model, you'll realize there's huge capital invested in this area. People are spending like hundreds of millions of dollars just to collect the demonstration data. And what they only use those data for is to do imitation learning, which I believe is such a waste. Because there's a lot of dynamics information and interaction information embedded in those largely collected data sets. We should be able to leverage those data to model the dynamic instead of just doing imitation learning. And really getting us towards this scalable data engine and also scalable evaluation engine. And on this direction, again, we're still trying to identify the recipe and not trying to see where on this axis we should lies in, and that give us the right levels of structures and also the right levels of scalabilities. Specifically, one work we recently did also is a paper we're going to present at ICCV. It's called Phase Twin, which is actually in between this graph-based neural dynamics model and also this NVIDIA physics-based models. And here's actually how the results look like. On the left is our input video, just a few seconds of real-world interactions. And we'll be able to build a digital twin of this object. The digital twin, what we mean, contains the geometry, appearance, and also the dynamics of this object. In the middle, what we're showing are the reconstructed geometry that are tracked over time. We're using the color to show this tracks its persistence over the interactions. We also have a number of red points on the human hands, indicating the reconstructed actions. On the right, we have the foreground and the background. The foreground shows our action conditions, open loop, 3D video prediction. And we render the video from exactly the same viewpoints from the left video, the captured data. We render the video and overlay the video with the original video shown on the left. And that composed video is what's shown on the right. You can see how nicely the foreground aligns with the backgrounds. Shows the accuracy and fitting power of our dynamics models and allows you to align very nicely with what's happening in the real world environments. And here's how the framework in general look like. On the top left shows you the data we get through the interactions, which is just 3 camera views, taking RGBD video streams from this kind of interaction. And our model is actually using a physics-informed prior in the structures of spring mass. You can imagine we have very dense particles, and on the dense particles, we have a spring mass that's connecting between those particles to regularize their motions. And on the right, we show our optimization objective, which including the objective on the geometry the objective on the motion, and the objective on the render. And this work actually benefits a lot from the whole development of vision foundation models, where the geometry actually will leverage some single image 3D reconstruction models like Trellis. And for the motion, we take advantage of the Code Tracker 3, although we fuse everything into the 3D space to give you more holistic and coherent tracking over the 3D area. And for the rendering, we use Gaussian spline. And in this case, obviously, the object is a deformable object. So the Gaussian has to move together with the movements of those particles. For that purpose, we use linear blend skinning, where each Gaussian is associated with like one or a few of the particles. And because of movement of the particles, which also allows you to move the Gaussians around to give you the rendering for the deformable object. And after you have the digital twin, obviously, the most simple thing you can do is to randomly interact with it. Here we show you a keyboard and a mouse interface that allows you to interact with this deformable object after it has been constructed. You are highly encouraged to come to our posters, where you'll be able to do like live interactions with this deformable object. It also applies to many other objects like clothes, stuffed animal, rope, etc. And in the end, I'm a roboticist. So I would like to put this fish twin near my robots. And here are some of the interesting video we are able to get. Here on the top left, we have a teleoperation device that captures the real-time instructions by the human operator. And we are playing the captured motion in real time, both on the real robots shown on the bottom left, as well as on our digital twin shown in the foreground of the screen. You can see that this captured like motions applied both in the real environments and the digital worlds. They align very, very nicely with each other. Where in the screen, you can see the foregrounds overlays very nicely with what exactly happens in the real environment. And this video essentially shows two things. One, like our digital twin is running in real time because we implemented everything using NVIDIA Warp that allows you to leverage the GPU acceleration. And second, it is very accurate that even if you're running the digital twin in real time, it aligns very nicely with what exactly happens in the real world environments. And then we take a step further by not just digitalizing the objects, but also digitalizing the environment. Here on the left is the digital world. On the right is what's happening in the real world environments. Exactly the same robot motion running the digital world on the left and the real world on the right. They align very, very nicely with each other, both in terms of the appearance of the environments and also in terms of the dynamics of the environments. And then we can use this engine as a scalable evaluation engine. The reason we do this is because I have a lot of friends at Google Robotics and Physical Intelligence. One of the key bottlenecks they are facing right now in developing their robotic foundation model is be able to do scalable evaluation. If you think about institutions as big as Google and they are doing deep learning, you might be thinking they're probably evaluating hundreds, if not thousands of checkpoints every day. But in reality, for this type of robotic model, what they can only do are just a handful of checkpoints they can send for evaluation. And they have to wait for 2 days for the results to come back. And their exact words to me was, we have large enough budgets such that we can still make progress. This is what they were talking about when they are describing their Gemini robotics, which currently is still in this tabletop environment. I'm pretty sure the progress will diminishing as we move to larger scale and longer horizon tasks. So evaluation is a huge bottleneck for iterating this robotic foundation model, which is a huge pain for roboticists compared to, for example, people developing large language model or vision foundation model. Because the speed at which you can do the iteration is multiple orders of magnitude slower compared to the vision and language domains. So we're trying to use our digital environments to provide you with this scalable evaluation engine. So we streamline everything. We take a phone, moving around the robots to digitalize the appearance and also the geometry of the robots and the surrounding environments. And we're also digitalizing the objects that the robots are going to interact with. And after this digitalization of the appearance and geometry, we have to align two things: the color appearance and also the dynamics. For the color appearance, here the first row shows the images captured by a RealSense camera. If you ever work with robots, you know like RealSense is a very commonly used camera people use in the robotics domain, which gives you very weird color. Here on the top row, the color is shifted. The second row shows the rendered image from this iPhone captured reconstructions of the environment. And the last row shows our aligned results by doing this color alignment. You can see the first row and the last row aligns much better with each other after this alignment procedure. And then obviously we have to also model the dynamics. So what we did was very similar to face twin, where we take a few seconds of real world interactions. So on the first row, and based on this data, we digitalize the dynamics of these objects. Here on the second row, the foreground shows you the open loop future prediction that overlays with the original video. It shows you the accuracy of our reconstructed digital twin. Then we can put the things together. Here on the left shows you the simulation states, and on the right, which shows you the simulation results plus the rendered image that allows us to make use as inputs to our policies. And we are starting to do evaluation. This is a policy we start evaluating. This is a similarly simple like a policy that basically route this rope onto the cliff. This is running autonomously in the real world scenario. And these are the inputs to the policy. We have one externally mounted camera shown on the left and one wrist mounted camera shown on the right. Based on this two video stream, the robot is able to do this task using imitation learning. And this is exactly the same policy, trained with only real data. There's no co-training at all. The policy has everything, are only the real data. And we, out of the box, evaluating the policy. And the policy can give you very correlated behaviors in our digital environments, like by showing you can route this rope successfully into the cliff. And obviously, you can also evaluate many other policies. Here on the left shows you an external mounted cameras like viewpoints. On the right is a viewpoint from a wrist mounted camera. These are all running in the digital environments. These are not real videos. They're all running in the digital environments. The policy trained only with real data can perform very reasonably and correlatively in our digital world. And here, I want to show you our side-by-side comparisons. Here, the first row shows this evaluation and rollout results of our policy in the digital world. And the bottom row shows you the rollout results in the real-world environments. You can see how correlated their behavior is in terms of like doing this kind of deformable object manipulation tasks. It's just in the digital world, we can scale everything up. We can randomize the placement of the objects, randomize the configurations of the environments, which allows us to do more scalable evaluation of those robot policies. And here's the type of correlations we are able to achieve. Here we have three tasks. And the horizontal row shows you the success rates in the real world scenario. And the vertical axis shows you the success rates in the digital world. We evaluated a number of like policies, like action chunking transformer, ACT, diffusion policy, DP, as well as this model like a Pi0 from like physical intelligence. Like all of these models actually shows you very correlated behaviors in both the digital worlds and also in the real world scenarios. And this actually is something significant in robotics, because if you can remove half of the checkpoints from your evaluation queue, you have to do the evaluation for in the real world environment. That's huge cost savings for the developments of robot models, which actually is one of the key difference between the robotics and also computer vision. And for anyone who is doing evaluation, who claim they are doing evaluation in robotics, they have to be serious about the protocol they use to do the evaluations for their robotic policies. This is because there is only a limited number of policies or rollouts you can do in the real world scenarios that typically give you very, very high variance. Depending on how you set up the initial configuration, depending on how the lighting conditions are looking like, the results can be very different if you are even evaluating exactly the same type of policy. These are the papers I really like from Toyota Research Institute, especially as led by Professor Russ Hedrick at MIT. It really provides you with some kind of protocols you should follow in order to do more empirically rigorous evaluation of your robot policies. So just give you some kind of like impressions. For example, one thing we do is you have an overlay shown on the top left. We are placing the object in the real environments that fits with the overlay. What does that give us? What this gives us is this exactly the same or as close as possible initial configuration that is consistent between different checkpoints of the same policy, as well as between different policies, and also between the digital worlds and also the real world environments. It's just in the simulation shown on the right, we can do this at a much larger scale compared to do the evaluation in the real world scenarios. And obviously, because of all the efforts we put in aligning appearance and also in aligning the dynamics, our correlation show using the blue dots aligns much better with than the, for example, the ICCV25 show using the orange corsings. And in our paper, we have also shown because of this specific correlation we're able to achieve, it gives us some very interesting practical implications on how we can select checkpoints for those robot policies. Here, different figures shows the combinations of the task and the robot policy we use. The horizontal axis shows you the different numbers of iterations, and the vertical axis shows you the success rates in both the digital world and also the real world scenarios. You can see that our digital evaluation aligns very nicely with the real world evaluations. Like for this example, the best performing checkpoints doesn't appear at the end, but somewhere in the middle. And our digital evaluation can be very handy for you to filter out the checkpoints that are hopeless for you to do the real world evaluations. And we have also doing different kind of operation, shows you that the color alignments and physics optimization obviously are important for you to achieve this type of alignments. And very recently, we have also been developing additional dynamics model that is able to model this kind of elastoplastic motions, where you can see this kind of like hinges that can both deform elastically and also plastically. We not only can model their dynamics, we also have an automatic and systematic pipeline to identify all the necessary parameters to establish this kind of correlation. Here on the left is the digital world. On the right is the real world scenario, like exactly the same robot motion. On the left, this is simulation, not animation. This is simulation. The inputs to our digital world are only the initial states and the subsequent actions. You can see the levels of alignments that we are able to achieve by having this systematic ways of building our digital world. So this is our efforts in going towards this kind of scalable evaluation engine using FaceTune. Another a recent work we've been doing is called particle grid neurodynamics. That is another recipe we are pushing forwards that is more on the learning side instead of more on the physics side. So specifically, we're also using this particle representation, or we compose this particle representation with this grid representation as inspired by this material point methods, where we allow this mapping from the particles to the grids and back from the grids to particles. It gets you the benefits of both worlds, where the particles give you this consistency and persistency over space and time, and the grids give you this a more global modeling and more global incorporations of those environments for you to do the future prediction. What we can get are systems where we only require, in this case, not a few seconds, but a few minutes of real-world interactions, where you take this teleoperation interface to randomly interact with this rope. And then we provide this kind of digitalization. On the left is Gaussian splatting, capturing the appearance and also the geometry. On the right, we show you this pure neural-based digital twin. This looks like dynamic Gaussian, but this is not dynamic Gaussian. This is action condition 3D video prediction, where we have this keyboard interface that is able to teleoperate the movements of the n effector. It's able to predict how the n effector will be moving around and how the rope will also be deformed over time. And it can also be applied to ropes, clothes, stuffed animal, and also cardboard box. And again, this looks like dynamic Gaussian, but this is not. It's essentially action conditioned 3D video prediction. So that actually comes to the end of my today's talk. So more specifically, what we have been developing is this dynamics model of the environments. I don't care whether we use more physics or more learning. To me, what really matters is this digital environments that correlates with what's happening in the real world environments. Meaning, if a model works better, if a robotic system, if a robot policy works better in the digital world, does it necessarily also work better in the real world scenarios? That's the key missing piece of many of the so-called embodied AI, embodied agents like benchmarks out there. People spend a lot of efforts building those embodied AI benchmarks. But if the problems of the correlation between sim and real hasn't been solved, the impacts of those embodied AI benchmark will be hugely limited in terms of the impacts in the robotics domain. You probably is already realizing that many of the so-called embodied AI benchmark, although they are targeted for robotics community, but really robotics community still is hesitates in trusting the results from those benchmarks, because the results from those benchmarks does not necessarily correlate with what actually will happen in the real world scenarios, which is very different from, for example, image nets. Meaning if a neural network works better on image nets, that means progress on deep learning and computer vision, at least for a few years. That is why image nets was significant. And we need similar things, but for robotics. And the correlation between sim and real is the key problem people have to resolve before we can have this claim on this benchmark. And obviously, after we have this benchmark that we know correlates with the real environments, we will further know the value that generated by the data that is coming from these digital environments. That is just this data and also evaluation. They come hand in hand, and all of them are governed by these key concepts of correlation. And my lab over the past many years are trying to identify this recipe and give us this correlation in unlocking some of these key bottlenecks faced by the current developments of general purpose robots. And I would like to thank all my collaborators, especially my students. Without them, it would be impossible to do all these works. And also, I would also like to acknowledge the sponsors of my lab. Without them, it is also impossible to do many of the works I'm showing earlier. And that's the end of my talk, and I'm happy to take any questions. Thank you.